Good morning, everyone. My name is Rashmi, and today I'll be presenting our work titled Security Analysis of Distributed Virtual Reality and Physiological Sensor Systems. Our research focuses on understanding how modern VR systems that collect physiological data can introduce new cybersecurity and also privacy risk, and how these attackers may exploit weakness in these systems. Now, first I'll explain what VR physiological systems are and why this security is of main importance right now. Next, I'll introduce our system architecture and the threat model. Then I'll discuss the attack services and the vulnerabilities that we identified. Finally, we'll briefly cover our experimental setup before moving to the interception results in the later slides. So, what are VR physiological systems? The VR physiological systems combine virtual reality technology with physiological sensing devices. Unlike the traditional VR application, these systems continuously collect biometric information from users while they interact inside a virtual environment. Examples of collected data may include heart rate, EEG brain signals, and motion or spatial tracking information as well. This information allows the system to understand the user's emotional and physiological state in real time. For example, if a user becomes stressed or excited, the VR environment can automatically adapt by changing visual effects, difficulty levels, or even interactions. While this creates highly personalized experience, it also means the system handles extremely sensitive personal information. So, why this security actually matters? So, today, security is important because VR physiological systems are increasingly used in critical domains such as healthcare, rehabilitation, pilot training, education, and adaptive therapy. The data collected by these systems is not ordinary user data. It includes biometric and health related information that may be protected under regulations such as HIPAA and GDPR. Previous research has shown that VR motion data alone can reveal private information such as user identity, speech content, and even virtual keystrokes. Similarly, intercepted physiological data can expose medical conditions, daily routines, and also behavioral patterns. The figure on the right shows a real world emotion adaptive VR implementation, where the physiological sensors feed data through processing the software into an emotion analysis pipeline, which then influences the actual VR experience. If attackers gain access to this pipeline, they could compromise both physiological privacy and also potential physical safety as well. Yeah, in this slide, we will talk deeper about the system architecture. The system consists of three major layers. The first is the data acquisition. We collect information from the MetaQuest VR headsets and physiological sensors such as Biopack Research Ring, which captures signals including heart rate, electrodermal activity, ECG, temperature, and as well as the motion data. Second, we have the data synchronization layer. Here, all sensors stream are synchronized using lab streaming layer, which is called as the LSL here. LSL is responsible for aligning multimodal data in real time. However, by default, LSL does not provide encryption or any kind of authentication. This becomes a major security concern. Third is the application layer. Unity, Python preprocessing modules, and the excitometer consume these synchronized data to create an adaptive VR experience. The key takeaway here is a multi device software platform and communication channels must work together, creating many opportunities for security weakness. After analyzing the architecture, we identified several major attack surfaces. The first is the LSL data streams. Since sensor data is transmitted without any encryptions by default, attackers can intercept or tamper with physiological information while it's being transmitted. The second is a third party SDK and Unity integration. Many VR applications today depend on external SDKs. If these components are outdated, compromised, or poorly configured, the attackers may exploit them to inject malicious code or even abuse the APIs. The third area is biometric data logging. Sensitive information such as heart rate and ECG measurements may be stored in plain text logs, creating opportunities for unauthorized access. Another concern is the external device communication, where weak SSL and TLS configurations can expose systems to man in the middle attacks. Finally, we identified weakness related to authentication and user consent, including weak access controls and inadequate mechanism for obtaining informed consent for biometric data collections. Together, all these vulnerabilities define the attack surface of VR physiological ecosystem. To evaluate the practical impact of these vulnerabilities, we developed the threat model. Our attacker is a network adjacent adversary. This means the attacker only needs access to the same local Wi Fi network and does not require physical access to the VR equipment itself. Under this assumption, the attacker can passively sniff LSL packet streams, inject or replay unverified packets, exploit insecure Unity SDK integration, and extract plain text session logs as well. The diagram highlights several attack points, including packet sniffing at the network layer, SDK or API injection risks at the integration layer, and access to unencrypted logs during storage or visualization. The attacker's ultimate objective is to capture synchronized biometric and spatial data, infer information about a user's identity, emotional state, as well as their behavior, and potentially manipulate the VR environment itself. The threat model serves as a foundation for the experiments and the interception analysis presented in the upcoming slides.
To evaluate VR and physiological security, we created a test environment using a MetaQuest VR headset and a BioPack ring sensors, as you can see on the top of the slide. Data from this device were synchronized through LSLs or live streaming layer and visualized using the accelerometer within the Unity-based VR environment. And so during the experiment, we collect motion data, physiological measurements such as heart rate and heart rate variability, and also sessions event markers. This setup has allowed us to analyze what informations could potentially be intercepted within the typical VR physiological deployments. So we first analyzed motion-related data that could be intercepted during the VR sessions. The intercepted logs contain headset positions, orientations, velocity, accelerations, and quaternion values used for tracking movements in three-dimensional space. From these records, an attacker could reconstruct how a user moved throughout the virtual environments and determine where they are looking or interacting with. Although motion data may appear harmless, but prior research has shown that spatial movement pattern can reveal user behavior and even contribute to identity interference. Um, and so the key takeaway is that the network adjacent attacker can capture detailed movement information without really requiring any physical access to the headset. In addition to motion data, we successfully intercepted physiological informations that generated during the VR sessions. The capture records include a heart rate measurement ranging from approximately 69 to 70 beats per minute, and RR interval values ranging between approximately 795 and 812 milliseconds from the user. And we also observed a session metadata, include the event marker label, experiment started. And together, these logs reveal much more than just raw sensor values. They provide a timeline of the user activity and physiological responses throughout the VR experience. This demonstrates that sensitive biometric information can be exposed through default data transmissions and logging mechanism if adequate security controls are not implemented. After analyzing the architecture and intercepted data, We identified 16 security risks across the VR and physiological system. Each risk was assigned a probability score and a consequence score on a scale of 1 to 5. And the probability measure how likely a risk is to occur, while consequence measure the severity of its impact. The assessment reviewed recurring concern involving wireless communications, authentications, data storage, and the third-party integrations. Throughout the assessment, we has narrowed down into four different risks that stood out of having the greatest potential impact, which are highlighted in red. These risks will be discussed furthermore in details in the next slide. So in this slide is a summary of the highest risk finding in our assessment, with the consequence very severe. And the first is the possibility of a man-in-the-middle attack caused by unencrypted wireless communications. An attacker could intercept or modify the physiological and motion data before it reached Unity or the visualizations tool. The second is sensor spoofing. Without a proper authentications mechanisms, an attacker could inject false physiological measurements, leading to an incorrect interceptions of a user emotional or health state. And the third is the most severe risk of a plain text storage of biometric data. If logs are stored without encryptions, sensitive information such as heart rate variability, EEG, ETA, and even event markers can be exposed for a long period of time. And finally, we has identified a lack of explicit user consent mechanism for biometric collections, and beyond privacy concern, this introduced a regulatory and compliance issues related to a framework such as the HIPAA and the GDPR. And with together, these findings really indicate that the biometric protections must be the primary focus for these kind of system, especially the virtual reality and physiological deployments. Based on the identified risks, we want to propose several mitigation strategies for the future implementations into our system architecture. And the first strategy is end-to-end encryption, which should be implemented for all LSL stream and sensor communications to protect data while maintaining the low latency required for immersive VR experiences. The second strategy is anomaly detections. It's a technique that can be used to identify spoofing attempts and malicious data injections. Cryptographic hashing can also help verify the integrity of a store session logs. And the third strategy that we want to include is a stronger authentication mechanism to deploy between a headset, sensor, and the software components. And the context-aware authentications combined with the behavior analytics can further improve the security of the system. And finally, we want SDK and APIs to be regularly updated and validated. Explicit user consent mechanisms should be incorporated for biometric data collections, and debug configurations should never be enabled in a productions environment. And I believe that together these mitigations really address the most critical vulnerabilities identified in our risk assessment. In conclusions, our work demonstrates that default VR and physiological deployments can expose synchronized biometric and spatial data through unprotected communications channels. In our experimental environments, a network adjacent attacker was able to observe the physiological measurements, motion data, and sessions metadata without requiring a physical access to the device. And the risks really extend beyond the traditional data theft because the exposed biometric and behavioral informations can enable user profiling, psychological manipulations, and potentially affect safety in critical applications such as healthcare, aviations, and training. And really looking forward to the future research, we should really focus on three key areas. The first area is adaptive encryption framework that maintain the low latency requirements of immersive XR system. Secondly is the context-aware authentications method that combine identity verifications with the behavioral anomaly detections. And thirdly is comprehensive security standard specifically designed for multi-model data stream in extended reality environments. And additionally, the opportunity to include the privacy preserving machine learning certification framework for VR physiological components and ethical guidelines for biometric data use. And that will conclude our presentations. Thank you for your time and attentions.